Okay, so phosphatases come effectively in two families. There are acid phosphatases, which have pH optima somewhere around pH 4 or 5, and then there are alkaline phosphatases, which have pH optima somewhere around pH 10 or 11. Now, I've been given a phosphatase enzyme, and I'm trying to do two things. First and foremost, to determine whether it's an acid or an alkaline phosphatase, and secondly, to determine precisely what its pH optimum is. So to do that, I've got a series of tubes which I'm going to set up at a variety of different pHs. So to start with here, I'm just putting water into the tubes. And now I'm going to add some buffer, which will ensure that the pH stays at the intended pH throughout the experiment. You'll see that I've actually got 3 tubes here, and I'm using 3 for each pH value that I'm going to measure. One of them is a control. In other words, I'm not going to add any enzyme to that. I will simply add water to make up the same volume. Right, so now I'm putting in the substrate that I told you about, 4-nitrophenyl phosphate, and I'm putting half a ml of that into each of these tubes. And half a ml of water into the control tube at the front to replace the enzyme that I shall then put into the other tubes. So I'm going to mix each of these tubes. And then I'm going to add half a ml of enzyme. Start my clock as soon as I've added enzyme to the first one. So I now have 1 control experiment and 2 duplicate tubes, which will increase the accuracy of my overall result. Right, I'm going to leave those for 5 minutes now to incubate in the heat block at 30 degrees, and that will ensure that the temperature stays constant throughout the reaction as well. At the end of the reaction, I'm now going to add a concentrated alkali solution. So this is 1 molar sodium hydroxide, and the effect of that is going to be that it will denature the enzyme. So it will stop the reaction, and I will then be able to measure how much the absorbance has changed during the 5-minute period. And from that, I'm then going to be able to calculate reaction rate. Now, you might want to think about what assumption I'm making in deciding that I'm going to take the reaction for 5 minutes and then stop it. This is what you call a discontinuous assay. So I'm not monitoring the change in absorbance as I go along. I'm simply picking a time period, stopping the reaction at the end of that time period, and then using that to calculate reaction rate. So think about that while I do the rest of the experiment as to what assumptions I'm making, because it's really important that when we make assumptions in science, and we do it all the time, but we have to be quite clear what they are, and we have to ensure that those assumptions are entirely justifiable. Okay, so that's my final set of tubes completed. And I can look here now and add these to the other ones that I've done. These are at pH 5, 6, 7, 8, 9, 10, and 11. And if I hold those up, you can see that there is a noticeable difference in the colours. So now what I need to do is actually check the absorbance using this spectrophotometer here. So the first thing that I need to do is to zero the spectrophotometer. In other words, set it up so that the only thing that it's going to measure is actually the absorbance of the thing I'm trying to measure. So not the enzyme, if it has any absorbance at the relevant wavelength, not the little plastic cuvette, which doesn't necessarily have zero absorbance at any wavelength. So I've set this up at 405 nanometers. Okay. And now I'm going to use my control tube to zero the spectrophotometer. So what it's now doing is saying that everything in this tube except the thing I'm trying to measure, in other words, the 4-nitrophenol, which shows the yellow color, is simply removed from the equation, if you like. So if I look at the highest, the most brightly colored one, if you like, and I can check the absorbance of that here. And you can see there that that's giving me an absorbance of 0.555. And what I'm going to do then is I'll measure all the others. Then I will take an average of my duplicates and I will plot the resulting values out on a graph, and we'll be able to see that in a moment. So in the cuvette that I've put into the machine, I've got buffer, the substrate pyruvate, and the NADH. And if you look at the readout, you can see that it's already giving us an absorbance value of about 0.68, which is due entirely to the NADH. And now I'm going to add some enzyme to this. And this time, this is a continuous assay, because I'm going to be able to use the chart recorder to record the absorbance change as it happens. So we can see the pen moving down as the absorbance of the NADH decreases because it's being used up. So as the reaction goes along, NADH is being converted to NAD. And as I said earlier, NADH absorbs light at 340 nanometers, but NAD doesn't. So as the conversion happens, the absorbance goes down. We can see as this goes, that to start with, the change in absorbance is fairly linear. But we will also see, as the reaction continues, that it starts to slow down. And eventually, we'll reach a situation where there is no apparent change in absorbance. Think back to the question I asked you earlier when we were doing the discontinuous assay. What assumption am I making? And how would I go about making sure that that was genuinely true? It's tempting to assume that when the absorbance stops changing, this means that the reaction has completely finished. But actually that's not the case, because this is a reversible reaction, as you saw earlier. So what happens is that eventually the reaction reaches equilibrium. And that means that the forward reaction and the backward reaction are continuing at the same rate. So to all intents and purposes, NADH is being converted to NAD and NAD to NADH, but at the same rate, so the overall absorbance doesn't actually change. So now the machine is just printing out the information about the assay that I've just done, and you can see the graph that I've got. From this, I can now actually measure the change in absorbance. So I need to get a ruler and draw a line of best fit through the linear part of the graph. You can see here that it starts to tail off down here, and eventually, if I'd left it long enough, it would have become completely straight. And I can now measure off the change of absorbance here against the time that that's taken. And I can use that to calculate an absorbance in terms of change in absorbance per minute. And that gives me my rate of reaction. If I repeat this experiment with less substrate, so here I've made up a cuvette which contains a much smaller amount of pyruvate, okay, I'll stop that now. If I'd let it run on for a considerably longer period of time, you would have seen that, like this, the first reaction, this one also would have slowed down and reached equilibrium. But it would take longer in this case because the reaction is slower. So if I put them side by side, we can see there the considerable difference in reaction rate caused by the different amount of substrate.